Hello, and what we're going to try to see today is the ocean floor, actually bathymetric features of the ocean floor, features of the ocean floor if we could take the ocean actually away from the floor. The ocean was thought of to be for a long time completely flat because ocean water's ability to actually dissolve rock. We found in World War II, once we actually went through and had ships go across the Atlantic Ocean looking for German U-boats with sound waves. Sound waves would go down. If they didn't hit a U-boat, they would go all the way to the bottom. They would bounce back up, and we would actually get pictures of different geologic features or bathymetric features of the ocean floor. And then post-World War II, we actually found out that the ocean floor is more mountainous, more valleyed, larger and flatter plains than any place on dry land. Okay, so let's get to it. First thing I want to do is I want to draw a fictitious coastline. And this fictitious coastline will go over here from this side. We'll call this the west side of this ocean, the east coast of whatever landmass it is. And it goes down to a beach. And then it goes down to a relatively flat ocean, which we used to think was it. Then post-World War II, we found this great big mountain range in the middle of the ocean, to some more flatness, and we found deep ocean trenches, deeper than anything on dry land, and then we went all the way back up to the other side of the ocean, east side of the ocean, the west side of this continent. Let's go ahead and throw in some water. Nothing I'm drawing right now is to scale. What we'd actually notice is that these waves would all be over 1,000 feet, maybe even a mile high, and would inundate anything that's on the surface of the ocean, boats, whatever, maybe even planes. Okay, before we get too far into it, I want to draw a couple of atmospheric things which are there because of the ocean. Some cumulus puffy type clouds, some stratusy kind of clouds, and then maybe some even thin, wispy kind of cirrus clouds. And then what sky wouldn't be true without a sun smiling away. And I'm going to draw a couple little birds up there too. 3 of them, in fact. Okay, let's get back to the bathymetric features. Okay, we're going to start at this side. We're actually going to start about some things that actually belong to the continent. Continent basically is this block, which if I pick a different color, this block belongs to the continent, just sort of like this block belongs to the continent. So the actual only ocean floor is this area right in here. So we're going to start with this one right here. If you notice, I've got words down here. Rather than write the words, which would get really complicated and I'd have to write really small and very clear, I'm going to have the words down here. I'm going to put a number, like right here I'm going to put number 1, and number 1 coincides with number 1 down here because this is the continental shelf. Continental shelf is the actual underwater extent of the continent. If we had an ice age where we'd take a lot of this water, put it up on top of land, maybe down as far as Pennsylvania, Maryland, we would actually find that the ocean level would go down, maybe located right in this area, and this would be brand new land for the continent. Vice versa, if we have more glacial melt, we're going to fill this basin where the water will actually go up and we'll even have less land. Some estimates maybe even 150 feet higher. Right here in Northern Virginia where I'm located, my school is at an elevation of 170 feet, so we would pretty much have oceanfront property. So an underwater extension of the continent, right around here at about 150 meters, and we'll talk more about depth later. It drops off, not near as fast as it's drawn in this picture, but this is number 2. This is going to be the continental slope. Down here where it actually goes into this flat area, you can sort of see it changes slope. It gets a little more horizontal. This is going to be the continental rise. And then once we get in the continental rise, we're going to move on to this flatter area. This is the abyssal plain. abyssal plain is going to be number, let me actually just give this one number 4. We'll get back to 4 and 5. We'll give this one number 6. 6 is going to be this area, and you can see it's actually extended there up to this thing. It extends on this side, may even extend over on that side. I'm only going to write one number 6, but you can see that it does extend. Number 7, abyssal hills. Well, every once in a while on this ocean floor we have small little blobs. They can be lava, they can be some other things, but this is the abyssal hill. And let me write number 7 under that. If the hills get a little larger, we call them seamounts. And seamounts would look more like, let me make sure I got the right color. Seamounts are going to look more like this. They're going to rise from the abyssal plain, but they do not make it to the surface. Number 9, actually maybe volcanic islands, but on an island, that's going to be the same as a seamount, except this seamount grows up enough where it actually pops right out of the ocean. Hawaiian Islands can be an example of this, but it'll be a very special type of a seamount, which we'll talk about later on. Once it's up at the surface, these waves interact with it. If this volcano becomes extinct or doesn't erupt as quickly as it should, the water will actually wash the rock away faster than the volcanic action can replace the rock. It'll actually wear it down to the ocean level. Another thing called isostatic balance, because we actually build up this land. It's sort of like we put somebody inside this canoe. And the more mass we put in the canoe, the deeper the canoe gets. And any way we look at it, this mountain, if it doesn't keep growing, it's going to be a flat-topped underwater mountain, which we call a geo. And that's going to be our number 10. And I'm not drawing the numbers here very well. This is our number 8. This is our number 9. This is our number 10. Then we get to the mid-ocean ridge. Let me see if I can do something about that. If I can, actually, you can see the number 4. I'll be writing number 11 right here. Do I have the right color? Let me go ahead and just number these. There's 11. This is going to be our 12. This is going to be our 13. And our last bathymetric feature. And then I can just stick with this grayish color. Okay. Actually, no, I can't. We have this big mountain range. This mountain range is 47,000 miles long. It runs down the middle of most of the oceans and is called the ridge that runs down the middle of most oceans, the mid-ocean ridge. And mid-ocean ridge is number 11. In the center of the mid-ocean ridge is this valley. We actually now know that this plate, this is a plate. When we get to plate tectonics, this is moving this direction towards this continent. This all is moving this direction toward that continent, but it's going to have a really bad time right here. But anyway, this is called a rift valley. Rift means to pull apart, to separate. So this is our number 12. And then our last feature is the deep ocean trench. Deep ocean trench, which you can see all the way down here. This is our number 13. And a deep ocean trench happens when one continental plate is run into another one crustal plate running into another crustal plate, and where one is actually being thrown down underneath the other. And we'll talk about that a little later as well. Okay, if I can scroll down here, here's another picture of the ocean floor. You can see there's the shore zone, there's the continental shelf, there's the continental slope and the rise. It actually tells you get gravel and sand in this area, we get mud along here, and then we get clay and oozes. Ooze is just a nice way of saying mud with about 30% organic matter mixed in. Really squishy type materials. There's the abyssal plain, there's our mid-ocean ridge with its rift zone, there's a seamount. You can see that the picture actually goes a little farther, and the deep ocean trench would be over there, and then the far coastline is going to be on the other side. Here's some of the depths that we can talk about. The Continental Shelf We actually watch both of these at the same time. Continental Shelf, somewhere between 150 meters to 200 meters, maybe 300 kilometers wide, probably in most places not quite that wide, but in some places you can see it very wide. The slope actually starts going back down. You can see the slope goes 7 in 100. It's about a 7-degree tilt. That's about the steepest grade in a highway. If you ever see a 7% grade, you're probably getting a truck warning to check their brakes before they hit it. So that actually is not anywhere near what you see. This is more like a parking lot you would see in a shopping center where water's supposed to fall and roll off, but it still looks almost flat as a pancake. This is like a 7-degree slope. Right here we go to a much smaller slope, not even 1 degree. So again, these are not drawn to scale. We go all the way down to about 200 meters up there, 150 to 200 meters down to about 2,000 meters there, and then from 2,000 down to 5,000 meters deep, 5 kilometers deep. So abyssal plain actually is very deep. It's called abyss because it's dark, it's cold, it's a very lonely place, even for ocean life. Then the trench way over here, it's not really shown. That can be somewhere between 600 and 11,000 meters deep. You can see we actually have 26 trenches on the world. We have 3 of them in the Atlantic, where I pretty much live. We have 1 in the Indian, and we have 22 inside the Ring of Fire, the Pacific Ocean. Deep sea basins, 5,000 meters. Abyssal hills, abyssal plains, you can see those, not so much in this picture, but we did have them up here. Abyssal hills rise up to about 1,000 meters, so seamounts go up even higher. Islands go all the way to the surface, which can be in that 5,000 meter and maybe a little deeper, a little shallower, plus whatever it sticks up above water. Mid-ocean ridge, 400 kilometers wide, rises 3,000 to 1,000 feet. It actually does come up around Iceland. Iceland is a good example of where this thing actually does become an island, where this separation, where this molten rock coming up to the surface is coming up much faster than can be worn away by the water. And then the Central Rift Valley, 20 to 30 kilometers wide, cuts deep into that mid-ocean ridge, and that pretty much is the picture. I do want to show you something called the hypsographic curve, and I apologize for the size of this and the definition. What it basically does, it shows you how much of the land is actually above sea level, how much of it is below. And if you take a look, we have about 24% of the land that actually sticks above the ocean. So if we do the quick math, we have about 76% of the land below the water. If you take a look, the highest elevation goes up to about 8.75, actually 8.848, but 8.75, 8.8 range kilometers above. Deepest ocean goes down to 11 meters. So if you actually took the tallest mountain, turned it upside down, and put it into this deepest trench, you would still have somewhere around 2, almost 3 kilometers of water. So it would only reach up to about this level right here. It also shows you the relative depth of, you can see the slope, you can see the continental shelf, you can see the rise, the abyssal plain. It shows you the relative amount of the land that's going to be found any place else. And again, that's called a hypsographic curve. This is actually showing you scales. If you take a look at this picture, which is probably even less exaggerated than what I drew, they're actually telling you this thing is vertically exaggerated 10 times. So basically, if you took this down, there's twice as much. There's 4 times, 8 times. If you actually drew this in real scale, you'd find out that you're drawing almost a straight line across the top to represent even, this abyssal plain. Over here, we're doing the same thing, 10 times vertically exaggerated. So you may actually see a little bit of a depression right there, but it would be pretty much a flat area, something that we really couldn't see the definition. Here's one that actually is again 10, and you can see both things. So we actually have the shelf, we have the slope and the rise, which should actually be not This is exaggerated 10 times. We'd have to go up, and there's exaggerated twice, there's exaggerated 4 times, there's exaggerated 8 times, and going up there, exaggerated 10, about there. So that would be our deepest depth. At this location, you may see a couple little blobs there, but almost everything else would look like a flat line. Last thing in here, this is how you actually get number, let me go back up there for a second, without driving you guys too crazy. This is how we get number 4, submarine canyons and deep sea fans. If I could draw this in a 3-dimension, the deep sea fans would be anytime water is moving off this land, it carries rock material along with it. And what it does, it scours into this landscape. Because it's carrying all the rock material, it tends to be more dense than water and just keeps rolling and rolling and rolling. And again, remember, this is sort of like a steep hill that you've maybe seen for truck warnings, not anywhere near this steep, just like that's probably close as like a parking lot, flat as a pancake. So anyway, this is how we're going to get number 4 and number 5. And let me scroll back down. You get water coming out of the ocean, or out of the landscape, coming pretty quickly, bringing sediment with it. And what it does, it just rolls down, collects into relatively low areas, and you're going to get some coming out of there, and you may get some coming out of here. And it actually gets a pretty good flow, and it actually flows right down, digging into the Continental Shelf, the slope, and then producing this huge accumulation of talus. It's called an alluvial fan, but it actually makes this deep sea fan. And you can see here's one off the coast of the United States, Washington, D.C., about right there. This one's off the coast of New York, actually created by the Hudson River. As the Hudson River comes in, carries lots of material, but you can see there are other ones all along the coastline, but this is the one they're actually producing. And this is the Hudson Canyon, reaching all the way down to the abyssal plain, where we have abyssal hills. They're calling it the ocean floor, but you can see how big the continental rise is, you can see the slope, and again you can see the continental shelf. Hope this clarifies some things. Take care. Bye.